Hello, and welcome to lecture number 3 for music theory number 1, called Where Do Musical Intervals Come From? I'd like to point out this painting, which is a pretty nice one, by Fyodor Bronikov, called Pythagoreans Celebrate the Sunrise from 1819. And you may be wondering, who are the Pythagoreans? Why are they celebrating the sunrise? And what does it have to do with musical intervals? And hopefully by the end of this presentation, you will roughly know the answer to those questions. Introduction. Imagine that you live in a culture in which there are no musical scales and no musical instruments, but people do sing, and you want to measure the distance between sung notes. So first question is, why would you want to do this? Second question is, assuming you've figured out that you really did want to, how would you do it? So first question, why would you want to measure the intervals between the pitches? One reason is that you might want to build instruments that could replicate the same intervals, right? So if everyone in your culture is going around singing happy birthday and you want to invent an instrument that can also perform happy birthday, you're going to have to create pitches that are in the proper intervals with one another, right? You might want to also be able to write down your melodies and your harmonies with the appropriate degrees of precision. We saw in the previous video, and maybe a little bit in the one before that, that early on in Europe, there were only very imprecise ways of writing down pitch interval distances, right? Before there were lines on the staff, there were just those neumes, which just showed you rough little contours, but it would be impossible to read exactly what the interval size was between notes. So that would be another reason you want to measure the intervals. Just to go back one more note about that. If you're not writing down the precise intervals, or if you're not writing them down precise enough, someone can't read your notation and then be able to sing the song that you want them to sing. All they could do is maybe guess at what it's like if they already know the song. So if you want to be able to have someone read from notation and that notation be prescriptive enough that the thing actually sounds like what you want, then you have to be able to write down precise intervals. Okay, and then this third point, why you might want to measure intervals between pitches, is to help singers, instrumentalists, and composers to conceptualize musical structure. So, for instance, one of these things would be to categorize different types of pitch intervals. So we know this because we think about this a lot. We think about consonance versus dissonance. Consonance, you could define it in a couple different ways, but you could talk about consonances as being the intervals that are allowed between pitches, or certain intervals that are more stable than others, or even some that are more pleasant. I put that in quotes because I don't really believe in the pleasant, unpleasant thing, but that's how it's often defined, particularly in the scientific literature. In comparison, dissonance might be defined as certain sounds that are not allowed, or that have to be treated in special ways, notes that are, or sounds that are unstable, or sounds that are so quote-unquote unpleasant. Okay, so that's why you might want to measure intervals between pitches. But the next question is, how do you measure the intervals between pitches? And that is what we are going to be talking about. So, I don't know if you remember this little chart from last time. I used the Pratt software to map out the pitch contour of people singing this tune called Populus Zion, or Sion. So a first step in this would be, let's say we know this tune, Populus Zion, and we want to write it out and figure out what the intervals are in it. First step would be to try to identify the pitches. And a second step would be to measure how much higher or lower each pitch is relative to the previous pitch. So we're going to take a look at just this area in the box here. And there I've expanded it. And so we're doing the first step of identifying which are the pitches. So let's listen again. Okay, so I'm looking for roughly straight lines in the sound that they're producing in pitch space. And notice I am quantizing what they're doing. So around here, they're not staying exactly on that line, right? They're kind of coming below it and then going above. And then in here, there's a lot of variation that I'm just reducing out because I'm just trying to find sort of like the average. So and this is a big important difference between pitch in singing and pitch in speech, which I didn't put a slide in about this, but in speech, our pitch is always moving. It's pretty rare to speak just on pitches. When we do, it sounds artificial. It's much more common for us to move the contour around within each individual vowel or each syllable. But in music, we pretty much keep the contour flat, and that's why we can measure the intervals between pitches. So I zoomed in a bit for step 2, just so we can ask how we are going to measure, when we're going to measure how much higher or lower each pitch is relative to the previous pitch. So from here to there, we could look at that interval from the second pitch to the third pitch, and then from the third pitch to the fourth pitch. How far are these? So how would you measure those interval sizes? We figured out how to identify the pitches. We look for flat lines. But then how do we gauge that interval size? Over here, we just have frequency. Frequency wasn't really figured out until well into the Enlightenment. So, we definitely had musical notation long before we had any sense that a pitch that's around there is vibrating at 200 times per second. We didn't have any way of perceiving something that vibrates that fast up until, the Enlightenment around 1700. Let's go all the way back to Pythagoras in about 500 BCE. 500, otherwise known as 500 BC. Pythagoras. So Pythagoras was born in Samos, Greece, around 570 BCE. And then if you assume he lived 70 years, he lived to about 500 BCE, right? He was a huge influence on Plato. And Plato was older than Aristotle. I think he was Aristotle's teacher too. Anyway, Pythagoras definitely was a main influence on Aristotle, even though Aristotle disagreed with a lot of the things that Pythagoras stood for, while Plato sort of really identified with those things. But Plato and Aristotle are, you could say, the two hugest influences, except maybe the Bible, on medieval and Renaissance Europe, and so really just on Western culture. So the fact that they're both influenced by Pythagoras is very important. Okay, so Pythagoras comes up with this principle. Pythagoras is like a mystic. He has a cult, the cult of the Pythagoreans that we saw on the very first screen. But he was also a mathematician. You know him from high school, probably, from learning about the Pythagorean theorem, which is just a mathematical theorem about triangles. But he also just really believed in the mysticism of numbers and the mysticism of the structure of the universe and how that was related to music and musical intervals. So this principle of musica universalis is the belief that the planets move according to mathematical equations and thus resonate to produce an audible symphony of music. And that is just a quote from Wikipedia. The Wikipedia article on Pythagoras is great, so if you are curious, then just go take a look at that. Numerology, I wanted to bring this up. This is pretty much the concept of treating numbers as mystical, anything, and it doesn't have to be just pure number, but mathematics more generally. Beginning with Pythagoras and going all the way up until into the Enlightenment, so middle 1600s, it was a dominant thought that the universe, the cosmos, were attuned to, itself or one another in the same way that a musical instrument is attuned. And there was this idea that there was a macrocosm, which is the cosmos, and a microcosm, which is inside the human body, and that music is this binding between the macrocosm and the microcosm. So in this image here, this comes from the late Renaissance, early Enlightenment by Robert Fludd, around 1618, I think, but it's portraying the cosmos as a huge lyre, which is just kind of like a guitar, like a lute thing. But I would say this is more a monochord, but this cosmos is a huge lyre with crystal spheres or planetary orbits instead of strings. So this is actually just a monochord, which we're going to see in a second. But here's God tuning the monochord. And then these are all the ratios like fifths and octaves and fourths and tones and the musical notes. And this is down here is earth. So presumably this is the macrocosm up here with the sun in there. And then this is the earth. And the monochord, or the structure of music, is also the thing that is binding the structure of the universe there. That's an idea that, I mean, it seems old-fashioned to us, but if you think about it, if it was around from the time of Pythagoras in 500 BC, all the way, and pretty dominant all the way up until about 1600 of the Common Era, that's over 2,000 years. And who knows how long before Pythagoras it was a big deal. So, for how much we know about history, the extent of recorded history, I mean, it was around for 4/5 of what we could say is recorded history. So it's a pretty dominant idea. The idea that music is what binds the outer universe with like the inner soul realm. So why am I talking about this when it comes to intervals? Well, there's a famous legend. It's probably not 100% true, but there's at least some truth to it. It's true enough that it's actually a very good teaching metaphor. So this is the legend. Pythagoras is walking, he's strolling through the forest, and all of a sudden he hears these consonant intervals. Okay, so maybe he hears something like this. Right, so he hears some sounds like that. The notes I was playing were C and G, C and F, F and C, G and C. At one point I played F and G at the same time. So you'll see a little bit more of that in a second, why I chose those intervals. But he hears consonant intervals sort of happening at the same time, or like roughly the same time. Perfect octave, perfect fifth, perfect fourth, and then there's that whole tone in there between F and G. So he hears this kind of far off, right? And then he says, I wonder what that could be, and he walks towards it. And he finds it's a smithy, a smithy is just like where blacksmiths do their work. Blacksmiths pound metal into shape. So what he finds is that the sounds resulted from the weight and density of the hammer and not from the strength of the impact. So we basically, there's a big strong guy and a little strong guy, and their hammers are producing two different sounds, and he switches the hammers in the hands of the two blacksmiths. And the sound that they're producing, whether it's the C or this or that, whichever sound it is, stays with the hammer. It has nothing to do with who the blacksmith is that's pounding it, and it has nothing to do with how hard it's being pounded. It's something about the structure of the hammer itself. And then in the old legend, Pythagoras says it has to do just with weight, but it's a little bit more complex than that in terms of physics. And I've tried this myself, so I actually recommend you do it. You can go to Lowe's and just get some washers of different sizes and see, if the sound that they make goes along with the weight. And it doesn't exactly. There's some other things involved, but basically you can assume it does have to do with it's sort of a combination of the weight and density of the metal hammer being used. So what he does is he sees like it's not how hard each individual blacksmith is pounding the hammer, but it has something to do with the hammer itself. So he says, could I borrow these hammers? He does some experiments. He examines the hammer weight density and finds that the consonants correspond to simple ratios between the hammers. So let's just assume for a second he's just weighing these things. He finds this is obvious one, but if there's two hammers that are the same weight, they're going to produce the same sound, which is just a unison. If there's one hammer that's half the size of another hammer, right? Or you can say, well, one's half the size of the other one is 2 times the size of the first one, right? That's reciprocal. So it doesn't matter which way you do it. But then you produce an octave. So this is my big hammer down here and my little hammer down there. Then if he weighs the hammers that are producing a perfect fifth, And he finds that this lower one, the bigger hammer, is let's see, this littler hammer is 2/3 the size of this bigger hammer. So the perfect fifth is a 2-to-3 ratio, or 3-to-2, however you want to look at it. And the perfect fourth, he finds between these notes, and he finds that so this littler hammer is 3/4 the weight of this hammer. So now what he does is he says, like, I'm going to take these hammers home with me. And I want to perform some additional experiments to determine whether the same principle applies in other sorts of circumstances. So you can see this old woodcut. This is a very old woodcut, but I can't remember how old it is. It's medieval of some sort, maybe about 1000 AD, but I don't remember exactly when. So what you can see here is he has taken the weights, so imagine those are the hammers, and he's suspended them from strings, and now he's checking to see if those weights produce the consonances on the tension of the strings. Here he's using pipes and showing different lengths of pipe and trying to see if the length of pipe, if like a 3-to-4 ratio at length of pipe also produces the same consonances. Here he's got little glasses of water. That one's just a little bit full. This one's very full. Different sized bells, metal shapes. These are the blacksmiths themselves. So he does all these experiments, and he does find that the same principle applies to all instrument types. Now, it is important for the history of science. It's pretty interesting that for 2,000 years, nobody tested this. Or basically anyone who tested it didn't publish anything. So for 2,000 years, everyone was going around saying oh yeah, if you just hang hammers from strings, hang different weights of one weight that's twice the size of another one, you'll get an octave with strings. Vincenzo Galilei at the end of the Renaissance, he's the father of Galileo Galilei, actually tested this and found that's totally not true. So you have to do the square root of the weights or something like that in order to get the right ratio. And there's stuff a little bit different with each of these things. Sometimes the mathematical formulas are a little bit more complex, but the basic principle is the same. So even if an octave has to be 4-to-1, if you had to do the square root of 4 to get 2-to-1 here, right? That's still the same principle. It's just like one additional mathematical step. Basically, he finds that, so if you allow some little things like that, then the principle does apply to the mass or weight of something like a hammer. It applies to string tension, string weight, tension, length, so hanging the thing on the string, and how much tension that produces, or dividing a string in half, which we'll see, so the length of the string. The diameter of a pipe, and this is tricky because it's the length of the pipe, but it's also the diameter. Both those things matter. But generally, the main principle is that the simple mathematical ratios correspond to the consonances, or vice versa. The consonances, the things that we hear, and so we say, doesn't that sound pretty? Isn't that a nice little consonance? It turns out that if you measure it, in any of these ways, the measurement of a sound that sounds consonant is going to translate to a simple mathematical ratio between weight or tension or length, things like that. Okay, so here's a little example of the monochord. This is an instrument that was used since probably in ancient Greek teaching and definitely in the medieval era, even up into the Renaissance. As I mentioned before, it wasn't until the Enlightenment, so around 1700 or 1600s, that scientists were able to count the number of vibrations in a string. So these principles that I was just explaining about from Pythagoras, they were figured out long before it was possible to count the vibrations of a string, which turned out to be just a massively complex problem. So this is the instrument that was used to demonstrate the sorts of principles that we were just talking about, and the way it would work is in this instrument, this person has one string in the back that's long, and then there's a movable bridge. So here he's got the string divided in half. He's striking just half of the string and comparing it to the full length of the string and showing that that's an octave. And then you're going to see that for the other intervals. So this teaching goes back probably to the ancient Greeks. This is a quote from a book that I've been reading recently called The Neural Code of Pitch and Harmony. It must be emphasized, this is about Pythagoras, it must be emphasized that apparently never before Pythagoras had anyone attempted to derive natural phenomena using mathematics. It turns out, I should back up a second, when I went to grad school and we would have to do the history of music theory and we'd read about Pythagoras and how everybody believed Pythagoras for 2,000 years, it was just assumed that everything that Pythagoras said must be kind of silly, that there's no way that the structure of the universe could be based on the same principles as the musical consonances, and that there's no way that the structure of human biology could be based on the same principles as music, and there's no way that music could be something that sort of like unites the macrocosm, the cosmos, with the microcosm, the internal state of the human body and animal bodies even. Anyway, and now it turns out there's a lot of this stuff is actually weirdly true. So the planets do actually synchronize their orbits around the sun. Not completely 100%, but they do, at least in some cases. So an example of this is if you look at the orbits of Uranus, Neptune, and Pluto, so the outer planets of our solar system. Okay. So I have in my notes here that Uranus goes around the sun every 84 Earth years. Neptune goes around the sun every 165 Earth years. So that is an almost 2-to-1 ratio of Neptune to Uranus. So if Uranus goes around the sun every 84 years, 84 times 2 is 168. And Neptune is going around 165 years instead of 168. So that's a 2-to-1 ratio, basically. And then Pluto to Neptune is a 3-to-2 ratio. So the first one is an octave. The second one is a perfect fifth. Pluto to Neptune is a perfect fifth ratio. So Neptune is 165 years. Pluto is 256 years. So then if you take, Neptune's orbit of 165 years, you multiply by 3, divided by 2, you get 247.5. So almost 250 years. And Pluto's orbit is 256 years. So very close to a 1 to 2 to 3 ratio. And we'll see in a second why that would be the case. So this is something, it's not found in all the planets of the solar system. I mean, it is found in many of them. So within our solar system, Mercury goes around the sun 4 times for every time the Earth goes around the sun. And Mars goes around the sun 1 time for every 2 times the Earth goes around the sun, right? So those are similar as well. Those are octave relationships. The thing is that some of this stuff is possibly chance, but they know that some of this stuff is not chance. So one of the examples of it not being chance leading to this is the 1 to 2 to 4 ratio in the moons of Jupiter. And this was discovered by a guy named Laplace in the Enlightenment. And so it's called Laplace resonance. And basically what you can see here is that this is actually kind of similar to what I was saying about Mercury, Earth, and Mars. But we'll talk about it here. So Io goes around the sun the fastest. Then Europa, these are the moons of Jupiter. So that this goes around Jupiter, a unit of 1. So every 2 times Io goes around the Jupiter, Europa goes around once, right? So they line up there. Every time Europa goes around Jupiter, it lines up with Io. And you can see that the green mark is called a transit. And then Ganymede is going around the slowest, and for every 1 time Ganymede goes around, Io's going 4 times, and then Europa's going once. And so what's interesting about this is if the planets were ever all in the same place, if they all ever lined up here, the gravity effects might be too strong and they would crash into each other. But you can see the way they have this resonance is that if they weren't organized with one another, they would sometimes by chance end up all in a line and they would just crash into each other. So because they all exert gravitational effects. So in the same way that when you push someone on a swing, you can regulate their swinging cycle, the gravitational forces on these guys influence one another and sort of keep each other in these orbits. That's the idea, at least. And you can look this up on Wikipedia. At first, I really did not think that this could be true, but it turns out it is an accepted scientific fact. So check out the article on orbital resonance if this is interesting to you. The principle of orbital resonance is that orbiting bodies exert regular periodic gravitational influence on each other, with orbital periods usually related by small interval ratios. And that's the same thing that Pythagoras figured out with the musical consonances, at least. So, and this is Langner again from that book I was talking about, Neural Code of Pitch and Harmony. He says that obviously, to a first approximation, the whole solar system from Mercury to Pluto is subject to gravitational resonances and, as a consequence, to some extent, obeys simple harmonic rules. So, when I read that, I said oh, we have to go back and reinterpret Pythagoras. He might not be as completely wrong as he has been assumed to be for the last 500 years or so. And then this is also something that I was pretty shocked about, which is a statement by Langner again, that the early universe resounded with harmonic acoustic oscillations. The harmonic echo of the Big Bang can still be measured today. And I followed up by reading the sources that he's talking about. And this is a thing that in order to understand what was going on at the time of the Big Bang, we study some of the acoustic resonances that are still present from that early explosion. So, yeah, the universe is structured to some extent based on acoustic principles, the same principles that govern musical harmony. Here is an example of a planetary system that is not our solar system, it's a different one. But you'll see that all of these planets are governed by pretty fairly well-tuned ratios, although they're not perfectly well-tuned, as you'll hear. They're a little bit out of tune because over time the system has been running and it seems to have devolved a bit. A little bit about the Harmonic Series. You watched the video by Andrew Huang recently. The Harmonic Series is the main source of scientific theories of where the consonances come from. Simple ratio relationships of the consonances were first demonstrated with the monochord, like I mentioned, in ancient Greece and in medieval Europe. Things like dividing the string in half produces an octave above the fundamental, which is just the length of the whole thing. Dividing it in a third, or I should say 2/3 there, produces a perfect fifth. Dividing it in 3/4, or 1/4, but 3/4 is better, produces a perfect fourth. And dividing it in 4/5 produces a major third. And you can see that here. This is based on the physics of how strings vibrate. This is the thing that wasn't figured out until about 1700. But when you strike a string, it doesn't just vibrate over its whole length. It vibrates in half of its length at twice the speed. It vibrates at 1/3 of its length at 3 times the speed, etc. So when you place your finger lightly on a string and play a harmonic, you're blocking. If you place your finger here, you're blocking this lower sound. So all you get is the upper sounds above it, or actually anything that does divide in half. If you place your finger at the 1/3 point, you're blocking those lower sounds and only getting some of the upper harmonics. So that's why harmonics work the way they do, and that's why they're related to the musical consonances. Dividing it in 5/6 produces a minor third. Okay. In the Enlightenment, it was found that the same relationships hold between the number of vibrations per second, hertz, right? So hertz is 1 cycle per second, or 1 vibration per second. And so like if we say the entire string vibrates at 100 times a second, 100 hertz, so we have this guy going wong, 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 at 100 times a second, and that's like a low G-ish on the bass clef staff, around right around there, 100 times a second. Then half the string, this guy vibrates at twice that speed, so 200 hertz. Each third of the string is vibrating at 3 times 100 hertz, so that's 300 hertz. Each quarter of the string is vibrating at 400 times a second. Okay, that's how you would derive that. So, and this picture shows that a string vibrates not just in its whole, but simultaneously in each half at twice the rate, and each third at 3 times the rate, and so on. So this shows that the overtone series is not just like an abstract principle, but it is present in virtually all harmonic sounds that are heard. Remember in a previous presentation, I talked about how harmonic sounds are a little bit different from noise sounds. Harmonic sounds mean that the body of the instrument reinforces certain vibrations, and that's how you get a whole harmonic series. So if it's just a noise, like even a hand clap, there are vibrations in there, but they don't get reinforced, and so they don't produce a very strong harmonic series. But anything that sounds like a pitch does produce a harmonic series. Okay, and the consonances most commonly found in tonal music, therefore, like fifth, fourth, major third, minor third, etc., for the most part are present in any kind of vocal or instrumental sound. So if I just go, oh, you are hearing in that, you're not aware that you're hearing it, but you're hearing my vocal cords not just do the fundamental, but also the upper resonances. So I can even do it with using my voice to filter out different harmonics and bring out different harmonics. So okay, I'm doing this as my fundamental. Ooh. And I'm going to bring out different harmonics with different shapes of my mouth and face. One more time. So I don't know if you can hear, but I'm going bum 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 bum. Now, let's just look at this overtone series again. Here's the TRAPPIST 1 thing, and let me show you the pitches of these planets are being pulled from here. So there's no fundamental here. We're starting with pitch number 2. The next one, C, G, Okay, right. Slightly out of tune, 4th partial, 6th partial, the 9th partial. Right, 1/9 of the string would vibrate at this rate. There we get the 15th. Divide the string in 15 parts, you'd hear that sound. And if you divided the string in 24 parts, you would hear that. We're going to watch this again because it's so good. Okay, now, even this harmonic series, you don't have to understand fully right now. It's definitely a good idea to memorize it. If you're a brass player, try to get all these notes. This is considered your, is that pedal tone? I can't remember what the low tone is. But brass players tend to get all these guys, but you tend to think of this one as not usable or out of tune. But see if you can get a natural harmonic series, and I'll try to find a video on that at some point. And other players, if you play a string instrument, try out harmonics and see if you can get some of these sounds. Okay, so then this is the last set of screens before a conclusion. So I just want to show you these two charts, and you should try to draw these charts. I'm going to show you how the charts are made, but then try to draw them yourself. So basically get a chart that has 12 slots and write 0, or I guess that's 13 slots, 0 through the number 0 through 12. And you need 2 6s actually, so maybe it's 14 slots. So we put the number of semitones there. So 0 semitones be a unison. 1 semitone is a second. We're going to say what kind of second in a second. It's a minor second. 2 semitones is a kind of second. 3 semitones is a kind of third. 4 semitones is also a kind of third. 5 semitones is a kind of fourth, etc. Okay, all the way down to there. But then now we just want to say which ones. So 0 semitones is perfect unison. 1 semitone is a which kind of second? It's a minor second. 2 semitones is a major second. 3 semitones is a minor third. 4 semitones is a major third. Okay, etc. So you want to practice writing this out. Just get a piece of graph paper, or actually any kind of paper, and write 0 through 12 here and double the 6. Because for 6 is both an augmented fourth and a diminished fifth. And neither of those is more common than the other, so you need them both. So this table are like the general intervals, the most common intervals. And if the way you use this, you say, okay, a 1 semitone second is a minor second. A 5 semitone fourth is a perfect fourth. A minor sixth has 8 semitones. Right? A minor seventh has 10 semitones. Major seventh has 11 semitones. That's how you read the chart. I'd say normally do it from the left to the right, because the other chart, I think, helps us do it backward. But you want to be able to say, if a certain interval is a certain number of semitones, you want to be able to say what the most likely specific interval is. And with these terms, genus and species of interval, the genus is just whether it's a unison, a second, a third, a fourth, a fifth, and the species says what kind of second, what kind of third, what kind of fourth. Okay, now this is going to be the same information basically. It's a little bit richer in terms of detail, but we're just arranging it by this middle column, this unison, second, third, fourth, fifth. Okay, unison, second, third, fourth, fifth, sixth, etc. For this, we're now going to look at, for the unison, the most common is to have a perfect unison, but you could have an augmented unison. I guess you could have a diminished unison. I mean, those are always weird. Augmented unison is a strange one, so let's just ignore that for right now. But with seconds, you're usually going to have major second or minor second. Sorry, major or minor. But if you have a second that's smaller than a minor second, you're going to have diminished. And if you have a second that's larger than major, you're going to have an augmented second. Similarly with thirds, you usually have minor and major thirds, but you might have a third that is smaller than minor. In that case, it's diminished, and you might have a third that's larger than major. In that case, it's augmented. When you get to fourths, notice that you don't have major fourths or minor fourths, right? You just have a middle fourth, a perfect fourth, and then smaller than that is diminished, larger is augmented. Same with fifths. The standard fifth is going to be perfect, whereas you can go smaller than that and larger than that. With sixth, there's no standard sixth, right? So the sixth is going to be either major or minor, or you can get it even smaller than minor as diminished, and even larger is augmented. Sevenths, same thing, and then octaves again, perfect. So in here, it's important to note that the fourth, the fifth, the unison, and the octave are the perfect intervals. They have one main type, and then bigger and smaller are augmented and diminished. Whereas thirds, seconds, sixths, and sevenths, those guys they don't have a main type that's perfect. They only have either major or minor. And then you can still go smaller, bigger, and get diminished and augmented. So now what I was saying is do this again, write this out, unison, second, third, fourth, fifth, write out this column after that, write in whether it's perfect or major or minor for each one, and then also throw in that there could be diminished or augmented on each side of these things. And then finally write out how many semitones for each of these things. And this chart is more complex than this one because we've worked in all the augmented and diminished possibilities. In this case, we took semitones as our starter, and we said, okay, this is between 0 and 12 semitones. What's the most common interval for, if you have a 4 semitone interval, it's probably a major third. But here is different. Here we have a 4 semitone major third. We've also got a 4 semitone diminished fourth in there, right? So the ordering of semitones is a little bit more complex here. So let's take a look at this. Let's do seconds again. So a minor second we know is 1 semitone. A major second we know is 2 semitones, and we get that over here. Minor second, 1 semitone. Major second, 2 semitones. But if you have a second that's even smaller than 1 semitone, if you have a 0 semitone second, it's diminished. If you have a 3 semitone second, it's augmented. And this really does come up. The diminished second doesn't really come up all that much, but the augmented second does come up in one of the scales that we use commonly. So it comes up between scale degree 6, flat 6, and raised 7 in harmonic minor. So we'll work on this next week, but if we are in A harmonic minor, we'd have A, B, C, D, E, F, G sharp, A, and the interval from F up to G sharp ends up being 3 semitones. From F up to G sharp is 3 semitones, and it's a second. From any F up to any G is a second of some sort. So you do have augmented seconds fairly commonly. Diminished thirds you don't see all that often, but you could see them. So if it's a third and it's only got 2 semitones in it, it's a diminished third. If it's 3 semitone third, it's a minor third. If it's a 4 semitone third, it's major. If it's a 5 semitone third, this you really don't see very often, but it would be an augmented third. So on your own, copy out these charts, copy out this column, and then see if you can fill out the rest of the chart from memory, and copy out this column, and see if you can figure out the rest of the chart from memory, and then just keep taking a look back at this screen. And so for our conclusion, it isn't entirely crazy to think that the principles of harmony do have something to do with the principles governing the structure of the universe. Nor is it entirely crazy to think that the principles that govern both musical harmony and the structure of the universe also govern activity within the human nervous system. And I recognize that I didn't talk very much about that, but it's something that follows from my work on the neuroscience of musical processing. And I will maybe tell you a little bit more about that in future discussions. But the basic idea is, in the same way that the planetary orbits are oscillatory systems, right? Like they keep going around the sun, they're like, whoosh, 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 whoosh. I mean, it's a lot slower than that. But if you have one planet that's going whoosh, 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 and you have a second one that's going whoosh, 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 those are close enough, like in a 2-to-1 ratio, that they're going to coordinate with one another, and that the slower one might regulate the faster one, or vice versa. That same thing happens in the nervous system too. So if you have one small little neural circuit it's going to go much faster than that, but if it's going, but faster, and you have another one set, it's definitely possible for that slower one to govern the rate of the faster one, and vice versa. So it's the very same set of mechanics that just coordinate oscillations. They do govern how planetary bodies interact with one another. They do govern how neural ensembles communicate with one another and coordinate with one another. And they're the same principles that we use to determine what sounds in music we find to be harmonic, that these simple ratios between things 1-to-1, 2-to-1, 3-to-2, 4-to-3, etc. Those things, the ratios that make intervals sound consonant to our ears are the same things that, at least in part, govern planetary movements relative to one another, and in part govern how neural ensembles in our brains, in our nervous system, the whole nervous system, coordinate with one another. So you don't have to be convinced from this that Pythagoras was definitely right 2,500 years ago. But what I would like you to recognize is that the science of intervals is at least a very fascinating one. It's one that's not going to be limited to just music. It's something that can pay off for sort of anything that you might be involved in, especially in like physics and physiology. But there's a lot of ways in which the science of intervals, the science of musical intervals, is something that is not limited to just musical interest. And so I hope in this unit, as you're getting better at practicing science of intervals, or getting better at recognizing and diagnosing different intervals and creating them, that this is sort of inspiring to you that it's not just about trying to put a name or a label on a certain, pair of notes, but you're really doing something that's interestingly mathematical and like maybe even mystical. Maybe even, can help you experience the rising of the sun and the setting of the moon in mystical ways, sort of like with the ancient Pythagoreans. So, hope you have a good week working with intervals, and thank you for watching.